Aviation is one of the safest forms of transportation in the modern world. Yet when tragedy strikes, it captures the world's attention in an instant. Behind every crash headline lies a complex web of human decisions, mechanical systems, weather conditions, and sometimes pure chance. The central question that investigators, journalists, and the public ask again and again is whether the cause was pilot error or mechanical failure. The answer, in most cases, is not simple. It is rarely one or the other, but a chain of events where small oversights, design flaws, or lapses in judgment align in a moment of catastrophe. In this script, we explore some of the most famous plane crashes in history, examining the interplay between human error and machine malfunction, and how each tragedy reshaped aviation safety forever. The year 1977 marked one of the darkest days in aviation history on the Spanish island of Tenerife. Two Boeing 747s, one operated by KLM and the other by Pan American, collided on the runway in heavy fog, killing 583 people. It remains the deadliest accident in aviation history. The cause was a devastating combination of human factors: miscommunication between the tower and the KLM captain, language barriers, stress, and impatience. Captain Jacob Veldhuizen van Zanten, a respected and experienced pilot, believed he had clearance for takeoff when he did not. Fog obscured his view of the Pan Am plane still taxiing on the runway. When both aircraft realized the imminent collision, it was too late. Investigators found no mechanical issues, only human misjudgment amplified by unclear radio procedures. The disaster revolutionized cockpit communication, leading to standardized phraseology and the introduction of crew resource management, or CRM, ensuring that subordinates could challenge captains when safety was at stake. 2 years later, another tragedy unfolded that would expose the vulnerabilities of aircraft systems rather than the pilots. American Airlines Flight 191, a McDonnell Douglas DC-10, took off from Chicago O'Hare in 1979 and lost its left engine seconds after takeoff. The engine tore away, damaging critical hydraulic lines and slats, leading to an uncontrollable roll and crash that killed all 271 people aboard and 2 on the ground. At first, suspicion fell on the pilots, but investigation revealed a shocking truth. Maintenance crews had used an improper procedure to remove the engines, bending the pylons that attached them to the wings. A small crack went unnoticed until it failed under the stress of takeoff. The pilots did everything right, but the plane's systems failed them. The DC-10 was grounded worldwide until McDonnell Douglas redesigned the pylon assembly and Airlines revised maintenance procedures. This tragedy became a textbook example of mechanical failure combined with human procedural oversight on the ground, rather than in the cockpit. In 1982, Air Florida Flight 90 crashed into the icy Potomac River shortly after takeoff from Washington National Airport, killing 78 people. The conditions were treacherous: snow and freezing temperatures. The pilots failed to properly de-ice the aircraft and used reverse thrust during taxiing, which blew slush back onto the wings, contaminating lift surfaces. The Boeing 737 stalled seconds after liftoff and plunged into the river. This accident was largely attributed to pilot error, but it also reflected broader system failures, inadequate training for cold weather operations, and insufficient ground support. The image of rescuers pulling survivors from the icy water became a haunting symbol of how small procedural mistakes can have massive consequences. The FAA subsequently tightened de-icing procedures, and airlines enhanced training for winter operations, ensuring that weather-related accidents would decline significantly in the years that followed. In 1985, Japan Airlines Flight 123 became the deadliest single aircraft accident in history, claiming 520 lives. The Boeing 747SR suffered a catastrophic decompression after takeoff from Tokyo due to a faulty repair years earlier. The rear pressure bulkhead, previously damaged during a tail strike, had been improperly fixed with a single row of rivets instead of 2. Over years of pressurization cycles, the weakened structure gave way, blowing off the tail and severing all hydraulic lines. The pilots fought to control the plane for over 30 minutes, but with no hydraulics, they were effectively flying blind. Their skill and composure were remarkable, but they could not overcome the mechanical destruction. Investigators traced the fault directly to Boeing's maintenance repair, leading to sweeping reforms in quality assurance and inspection oversight. The flight became a tragic demonstration of how human error on the maintenance floor, not in the cockpit, can doom even the most skilled pilots. Fast forward to 1988, when Aloha Airlines Flight 243 suffered an explosive decompression mid-flight. The Boeing 737's fuselage roof tore away, exposing passengers to the open sky. Miraculously, the pilots landed safely with only one fatality, the flight attendant closest to the rupture. The cause was structural fatigue from years of flying short island hops under humid, salty conditions. It was not a pilot error, but a failure in design assumptions and maintenance inspections. The accident highlighted the importance of aging aircraft management, leading to the Aging Aircraft Program in the United States, which required rigorous structural inspections of older jets. The early 1990s brought the case of United Airlines Flight 232, one of the most studied examples of both failure and heroism. A DC-10 en route from Denver to Chicago suffered an uncontained engine failure, which severed all three hydraulic systems. The aircraft became virtually uncontrollable. Captain Al Haynes and his crew, aided by a training pilot sitting in the cabin, used differential thrust to steer and slow the aircraft. Despite their efforts, the plane crash-landed in Sioux City, Iowa, killing 111 but saving 185 lives. The NTSB concluded that a manufacturing defect in a fan disc led to the failure. No one could have predicted or prevented it. Yet the pilot's teamwork and composure turned a total loss into a miracle of survival. The accident became a case study for crew resource management, showing how communication and cooperation could mitigate the worst mechanical failures. In 1996, the world watched in horror as TWA Flight 800 exploded minutes after takeoff from New York. Early speculation ran wild: missile strike, terrorism, sabotage. But investigators found the cause to be far less sinister, yet deeply troubling. A spark in the center fuel tank ignited flammable vapors, caused by faulty wiring and design flaws in the Boeing 747's electrical system. This mechanical failure was a wake-up call about aging aircraft wiring and fuel system design. The FAA subsequently mandated inerting systems for fuel tanks, preventing oxygen buildup and reducing explosion risk. While pilots had no control over what happened that night, the tragedy changed the way engineers thought about fire prevention inside aircraft structures. In 2000, Concorde, once the pride of supersonic flight, met a fiery end outside Paris. Air France Flight 4590 struck a strip of metal on the runway, dropped by a previous aircraft, which ruptured a tire. A piece of rubber hit the fuel tank, igniting a catastrophic fire. The Concorde, already overweight and struggling to accelerate, never gained enough speed and crashed into a hotel, killing 113 people. While the pilots fought valiantly, the crash was triggered by a chain of mechanical and procedural flaws. Debris on the runway, vulnerable fuel tanks, and operational decisions under pressure. The investigation led to reinforced fuel tanks and improved runway inspection procedures, but the damage to Concorde's reputation was irreversible. Within 3 years, the supersonic jet was retired, marking the end of an era in aviation. The 21st century brought its own share of tragedies that challenged assumptions about both pilot competence and aircraft reliability. In 2009, Air France Flight 447, an Airbus A330 flying from Rio de Janeiro to Paris, vanished over the Atlantic. When the wreckage was found, investigators discovered that pitot tubes had iced over, causing the autopilot to disconnect. The pilots, confused by contradictory speed readings, pulled the aircraft into a stall and failed to recover. The crash killed all 228 aboard. While the initial trigger was mechanical, the iced sensors, the ultimate cause was human. The pilots did not recognize a high-altitude stall and applied incorrect control inputs. This event underscored a dangerous gap in pilot training in the era of automation, where reliance on autopilot had eroded basic flying skills. The tragedy led to major reforms in manual flight training, especially for high-altitude stall recovery. Another chilling reminder came in 2014, when Malaysia Airlines Flight 370 disappeared without a trace. Despite years of searching, the main wreckage has never been found. With limited evidence, investigators proposed multiple theories: a deliberate act by the pilot, a rapid decompression event, or a catastrophic electrical failure. Without conclusive proof, MH370 remains a haunting mystery that blurs the line between human and mechanical causes. The disappearance reshaped global tracking standards, leading to the introduction of real-time flight monitoring systems designed to prevent an aircraft from ever vanishing again. That same year, Malaysia Airlines faced another tragedy with Flight 17, shot down over Ukraine by a surface-to-air missile. This was no mechanical or pilot error, but a geopolitical catastrophe, reminding the world that even the safest aircraft cannot withstand the dangers of war zones. In 2015, Germanwings Flight 9525 revealed one of the most disturbing human failures in aviation. The co-pilot locked the captain out of the cockpit and deliberately crashed the Airbus A320 into the French Alps, killing all 150 aboard. Technically, there was no mechanical issue, only a psychological one. This forced the industry to rethink mental health screening for pilots and change cockpit security protocols, balancing safety from terrorism with protection from internal threats. It showed that the most advanced aircraft and systems could still be undone by human intent. The Boeing 737 MAX disasters of 2018 and 2019 reignited the debate between pilot error and mechanical failure in a modern context. Lion Air Flight 610 and Ethiopian Airlines Flight 302 both crashed shortly after takeoff, killing 346 people combined. Investigations revealed that a new automated system called MCAS repeatedly pushed the nose down due to faulty sensor data. Pilots, unaware of the system's behavior, struggled to regain control. Boeing had failed to disclose the system's existence in training manuals, and regulators had allowed minimal pilot instruction. These were systemic failures, mechanical in design but human in accountability. The entire global fleet of 737 MAX aircraft was grounded for nearly 2 years. The scandal forced Boeing to overhaul its safety culture, redesign the system, and rebuild public trust. It became a defining case of how automation, when poorly integrated, can create more danger rather than less. Every one of these tragedies tells a story of intertwined human and mechanical factors. Even when a part fails, a procedure, a decision, or a culture often lies behind it. Aviation accidents are rarely caused by a single error. They are the culmination of unnoticed flaws converging at the worst possible moment. From the cockpit to the maintenance hangar, from engineers to air traffic controllers, every link in the chain matters. Today's aviation industry operates with an unmatched level of safety, largely because of the lessons learned from these very disasters. Each crash led to new technologies, from ground proximity warning systems to fly-by-wire redundancy, from CRM training to automated weather sensors. The margin for error has become smaller than ever, yet human vigilance remains indispensable. As automation deepens, pilots must retain their manual flying skills, understand their aircraft systems intimately, and trust but verify every instrument reading. Engineers must anticipate the unimaginable. Regulators must stay independent and uncompromised. And passengers, while often unaware of these layers of safety, benefit from a system that has been rebuilt, reformulated, and reinforced by the lessons written in tragedy. So was it pilot error or mechanical failure? In truth, aviation has shown us that it is almost never one or the other. Machines are extensions of human design, and humans rely on machines to amplify their abilities. When either side falters, the results can be catastrophic. But from each disaster rises progress, born of investigation, accountability, and an unyielding determination to ensure that those who perished did not do so in vain. Every check, every inspection, every training simulator is a silent tribute to the lessons learned at terrible cost. The skies are safer not because perfection was achieved, but because imperfection was studied, understood, and relentlessly corrected. The next time an airplane takes off, slicing through clouds thousands of feet above the earth, it does so on the wings of knowledge forged through decades of tragedy and discovery. Behind that smooth flight lies a story of pilots who acted bravely, mechanics who worked tirelessly, engineers who redesigned tirelessly, and investigators who pursued truth through wreckage. The debate between pilot error and mechanical failure will continue. But the reality is that both are reflections of the same fragile balance, between human ambition and human limitation, between the power of technology and the responsibility of those who wield it. And as long as that balance is respected, every flight becomes a quiet testament to the resilience of human learning and the enduring quest to make the sky a safer place for all.